This lecture is devoted to approximations of binomial and Poisson distributions by normal distribution. Let me remind you central limit theorem. So we consider random variable x which has any distribution. So x can be discrete and continuous, doesn't matter. Let's consider samples of size n. Then sample distribution of sample mean, which equals to 1 over n, sum of x i's. X i's are entries in sample random variables representing entries in sample of size n. Then distribution of sample mean x bar tends to normal distribution with expected value which coincides expectation of x, and variance which is given by variance of x divided by sample size n. Similarly, if we consider sample sum S, which is given by sum of entries in the sample, then distribution of S also tends to normal distribution with expected value equal to n times expectation of x, and variance is n times variance of x. So these both tendencies appear when size of sample tends to infinity. If n is large enough, then distribution of x and distribution of s are roughly normal. Now we will see how central limit theorem is applied to random variable x which has binomial distribution. As a starting point, we will consider random variable y, which is a discrete random variable and can have two values, 1 and 0. Probability that y equals to 1, let's say p, and probability that y equals to 0 is 1 minus p. Sample sum, we will denote it by x, for sample of size n. According to central limit theorem, distribution of x is roughly normal distribution with expected value given by n times expected value of y, and variance is n times variance of y. On the other hand, if y equal to 1 means success and y equals to 0 failure, then x is number of successes in n trials in binomial experiment, and this should have binomial distribution with number of trials n and probability of success p. Thus, this binomial distribution converges to this normal distribution. Let us find expectation of y. I think you can do it, but I will just, as an exercise, I will illustrate it here. This equals to probabilities sum of y i's times probability of y equals to y i's for all possible values of yi. This is 1 times p plus 0 times 1 minus p, which is p. And variance of y equals to expectation of y squared minus expectation of y squared. You can easily find this is p, and this is p squared. We found it, minus p squared. So this will be p times 1 minus p. And thus this normal distribution for x will look like normal distribution n times expectation of y, which is p, and n times variance of y, which is p times 1 minus p. And on the other hand, x has binomial distribution, so this is, let's put it like this, binomial and p. If you remember, np is expectation for binomial distribution, and np times 1 minus p is variance for binomial distribution. Thus, to summarize this, if x has binomial distribution with number of trials n and probability of success p, then expected value of x is np, variance of x is np times 1 minus p. We have derived this earlier, you can find it in corresponding lecture notes. And then binomial distribution can be approximated by normal distribution with expected value np and variance np times 1 minus p. What we got? This is discrete distribution, and this is continuous. And therefore we have one obvious problem. Probability that x equals to xi non-equal to 0 if xi is one of these numbers 0, 1, and so on, n. It is for binomial distribution. But probability that x equals to xi equals to 0 for all values of xi for normal distribution. There is a way to overcome this problem, this discrepancy, and the way to overcome it, this technique to overcome this difficulty, is called continuity correction. For continuous variable x with probability density function f of x, say probability density function, integral of f of x from minus infinity to plus infinity is 1. It's what we know. If x capital is discrete, random variable x, we have something similar. Sum of probabilities for x capital equal to xi for all possible values of xi is also equal to 1. Thus, we can put it like this: integral from minus infinity to plus infinity of f of x dx equals to sum of probability that random variable, discrete random variable x has values xi. Our next observation is we know that integral of f of x dx from minus infinity to plus infinity is area under f of x, under this curve. On the other hand, sum of probabilities that x equals to xi is sum of areas of rectangles. Since probability that x equal to xi can be considered as area of rectangle of height p and unit base. Next statement is very important. If xi's are consecutive integers and discrete random variable, like discrete distribution of x, is approximated by normal distribution, binomial and p is approximated by normal, and p and p1 minus p, then we can expect that f of xi is roughly equal to probability that x equals to xi. This can be illustrated by the following plot. So let's say this is x-axis, y-axis. Assume this is our f of x for normal distribution is probability density function, and these are, let's say, 1, 2, 3, so on, I plus 1. These are values of p. Then area under curve f of x can be approximated by sum of areas of rectangles. These are rectangles, and so we have rectangle, for example, this. Each rectangle has height p, x equals to xi, and base from, say, xi minus half to xi plus half, so it will have unit base. And thus we can expect that integral of f of x dx from xi minus half to xi plus half will be roughly equal to probability that x equals to xi. And this is exactly what this continuity correction is about. Let us consider this example. For x binomially distributed with number of trials 16 and probability of success half, use a normal approximation to approximate probability that random variable equals to 9. So we have random variable which has binomial distribution with number of trials 16 and probability of success half. So this can be approximated by normal distribution. Normal, here we should have np. it is mean value for normal distribution, and here np times 1 minus p. So this is normal distribution, and p is 8, and then p times 1 minus p is 4. Or normal distribution with expected value equal to 8 and variance equal to 4. Now we introduce z-score, which has standard normal distribution, and it is given by x minus mu divided by standard deviation, x minus 8 divided by 2. Now probability that x equals to 9 for binomial would be equal to probability that x is between 8.5 and 9.5 for normal. And in terms of z-score, this will be equal to probability that z is more than 8.5 minus 8 divided by 2 and less than 9.5 minus 8 divided by 2. And this is equals to probability that z is between 0.25 and 0.75, which equals to probability that z is less than 0.75 minus probability that z is less than 0.25. And this is values of phi capital found from table for normal distribution. Phi capital at 0.75 minus phi capital at 0.25, and using table for normal distribution we find that phi capital of 0.75 is 0.7734, and phi capital of 0.25 is 0.5987, and therefore this probability equals to 0.1747. We can find probability that x equals to 9 for binomial directly. This is 16 choose 9 times 0.5 probability of success to the power of 9 times 0.5 probability of failure to the power of 16 minus 9 or 7. And this equals, if we calculate it, we find it equals to 0.1746 to fourth decimal place. And as we can see, this number and this number are very close. In this particular example, there was no big point in using normal approximation, because we can easily find this probability, the next capital equals to 9, using binomial distribution. But in many cases, normal approximation saves, using normal approximation saves time. So in this example, we consider random variable x, which has binomial distribution with number of trials 50 and probability of success 0.4. We want to find probability that random variable doesn't exceed 25. If we want to use binomial distribution, we will have to find 26 probabilities for x to have 26 different values, which is quite a long story. And in this example, it makes sense to use normal distribution and to find quickly probability that x capital doesn't exceed 25 using normal approximation. So what we have here, x can be approximated, distribution of x can be approximated by normal with mean value np and variance np times 1 minus p. So np is 20 and np times 1 minus p is 12. So we got x approximation has approximately normal distribution with mean value 20 and variance 12. Then probability that x doesn't exceed 25, this is for binomial, will be approximated by probability that x is less than 25.5. This is normal plus continuity correction. So, and this equals to probability. Now we introduce z-score, that z is less than 25.5 minus 20 divided by square root of 12. Or this equals to probability that z is less than 1.59, which is value of phi capital at 1.59, which is found from table for normal distribution, and this is 0.9441. Thus, we found quickly probability that x doesn't exceed 25 using normal distribution, using normal approximation. By the way, probability, if we would have to find probability that x is less than 25, this would be equal to probability that x is less or equal 24. And in terms of normal distribution, we would use 24.5. So probability that x is less than 24.5 in normal, not 25.5. Couple of comments on when normal approximation is good enough. Is good enough. So we know that n should be large. N should be large. Then p, if p is too close to 0 or to 1, our binomial distribution becomes asymmetric. And we know that normal distribution is symmetric, therefore p should not be too close to 0 or to 1. And these two statements summarized in the following. N times p should be large enough, for example, more than 5, or n times 1 minus p should be also more than 5. So you check these two conditions, and if these two conditions satisfied, the normal approximation for binomial distribution is reliable. Poisson distribution also can be approximated by normal distribution. Let's consider this case, normal approximation of Poisson. Again, let's consider random variable y, which has Poisson distribution with parameter lambda. We know for Poisson distribution that expected value of y equals to variance of y and equals to lambda. Again, we will consider some for samples of size n. I will call it x again. X equals to sum of yi's. And so at one hand it should have normal distribution. We remember this. This can be approximated by normal with n times expectation of y and n times variance of y, which is a normal distribution for n lambda and lambda. On the other hand, x has Poisson distribution also. Because x can be considered as a number of events, so in Poisson distribution y is number of events which take time at certain time interval t, and x is number of events during time interval, say n times t, where t was time interval for y. So it's important. If y has a Poisson distribution, x also has Poisson distribution. If y is described by lambda, which is average number of events during time interval t, then x is also has Poisson distribution with parameter which replaces lambda and gives average number of events during time interval nt. Therefore, x will have Poisson distribution with parameter n times lambda. Thus, what we got? We got x has Poisson distribution with parameter n lambda, and it can be approximated by normal distribution with mean value n lambda and variance n lambda. And this is normal approximation for Poisson distribution. So we can replace, if n lambda we will denote by lambda, then it will be Poisson distribution with parameter lambda, can be approximated by normal distribution, lambda, lambda. Mean value and variance are equal to each other. From our arguments, it appears that this approximation is good if lambda is large enough. Lambda should be large enough. And we can say, for example, that lambda is one of ways to estimate when approximation is good enough, good approximation. Here is an illustration of how normal distribution or normal approximation is used. Probabilities for random variable x which has Poisson distribution. So probability, again, distribution of x can be approximated by normal with mean value 20 and variance 20. Then probability that x is between 21 and 23 inclusive equals, this is for Poisson, equals to probability that x is more than 20.5 and less than 23.5 for normal. And this will be equal to probability that z, which has normal distribution, is more than 20.5 minus 20 divided by square root of 20, and less than 23.5 minus 20 divided by square root of 20. And this equals to probability that z is. You can finish the previous example by yourself. What is left is not difficult and was done many times. I want here to get to the next topic, which is about Poisson approximation of binomial. So far we have spoken about approximation of binomial distribution by normal distribution and approximation of Poisson distribution by normal distribution. And from here probably we can feel that we can somehow get from binomial to normal and from normal to Poisson, and therefore binomial can be approximated by Poisson. Let's check it in the following line of reasoning. So we have x, which has, say, binomial distribution with number of trials n and probability of success p. And this can be approximated by normal distribution with mean value np and variance np times 1 minus p. So here we remember that this approximation is good when np is large enough. Let's say np is more than 5. Now here we can say that this will be pretty much as normal distribution with parameters np and p, provided that p is very small, and therefore 1 minus p is roughly 1. And this can be represented as normal distribution with mean value lambda and variance lambda. Here lambda is notation for np, and about this we remember that Poisson distribution with parameter lambda converges to normal with mean lambda and variance lambda if lambda is large. Lambda was more than 15, we decided. All of this can be summarized in the following. Binomial distribution with number of trials n and probability of success p can be approximated by Poisson distribution with parameter np, provided that n is large enough, is large, and p is small. And observations show that n should be more than 50 and p should be less than 0.1. So with these restrictions, approximation is reliable. Approximation is good. Let us consider this example. Suppose x has binomial distribution with number of trials 60 and probability of success 0.05. Calculate probability that random variable x is more or equal to 3, first exactly using binomial distribution, then using normal and Poisson approximations to this binomial distribution. So correct value for probability that x is more or equal to 3 is 1 minus probability that x is less than 3, which is 1 minus probability that x is 0 minus probability that x is 1 minus probability that x is 2, which is 1 minus probability that x is 0 is 60 choose 0 times probability of success to the power of 0, and probability of failure, which is 1 minus 0.05 or 0.95 to the power of 60 minus 60 choose 1 times 0.05 to the power of 1 times 0.95 to the power of 59, and minus, here should be probability that x equals to 2, 60 choose 2 times 0.05 squared times 0.95 to the power of 58. And this, if we calculate all these numbers, it will be 1 minus 0.04607 minus 0.14548 and minus 0.2588, and this equals to 0.583, let's say, to third decimal place. So what we got here exact value for probability that x is more or equal to 3 using binomial distribution. Now we can find this probability using the normal distribution. So probability that x more or equal to 3 when x has binomial distribution is approximately equal to probability that x is more than 2.5 for normal approximation. So for normal approximation we know that mean value is np and variance is np times 1 minus p, which is normal distribution with mean value np is 60 times 0.05, which is 3, and np times 1 minus p, you can calculate it, it's 2.85. And another comment here, 2.5 comes from continuity correction. So this now equals to probability. Now we can use z score, we did it many times, z more than 2.5 minus mean value, which is 3, and divided by standard deviation, which is square root of variance, square root of 2.85. And this equals to probability that z is more than minus 0.3 roughly, and this equals to probability that z is less than 0.30. And this is value of function phi capital, which is found from the table for normal distribution, and this equals to 0.618 again third decimal place. Now we can evaluate this probability using Poisson approximation. Thus, probability that x is more or equal to 3 equals to 1 minus probability that x is less or equal to 2. And here for Poisson distribution we will have x, which has binomial distribution with np, can be approximated by Poisson, with lambda equal to np. So, and keeping this in mind, we can find out that this equals 1 minus probability that x capital is 0 minus probability that x capital is 1 minus probability that x capital is 2 equals to 1 minus probability that x equals to 0 is lambda to the power of 0 divided by 0 factorial times e to the power of minus lambda to the power of 1 factorial e to the power of minus lambda minus lambda squared divided by 2 factorial e to the power of minus lambda. And here we know that lambda equals to 60 times 0.05, which is 3. And this will be equal to 1 minus e to the power of minus 3, lambda to the power of 0 divided by 0 factorial is 1, minus lambda. So okay, if we put here minus here with plus 3 and plus 9 over 2. And this is equal to 1 minus 0.42319, which is equal to 0.577 third decimal place. Now what we got? Exact value for probability that x is more or equal to 3 equals to 0.583. It is binomial. Binomial 60 0.05. Then first approximation, probability that x more or equal to 3 equals to 0.618. It is normal. 3, 2.85. And last result, probability that x is more or equal to 3 using Poisson approximation is 0.577, and this is Poisson approximation with parameter 3. We see that normal approximation not particularly good, while Poisson approximation seems to be fine. We remember that for normal approximation to be good, we need to satisfy this condition, n times p should be more than 5. But what we have here, n times p is 60 times 0.05, which is 3 less than 5. It is y normal approximation here is not very good. On the other hand, for Poisson approximation to be good, we need n to be more than 50 and p to be less than 0.1, and both satisfied, both conditions satisfied here. And this is why Poisson approximation is good.